Imagine that the greatest invention in aviation was not a faster engine or a deadlier weapon. Imagine that it was a shape. In the 1930s, rediscovered American engineer Jack Northrop built it and watched the world refuse to fly it. California, 1939. American aviation was entering an age of scale and urgency. Factories expanded, military contracts multiplied, and aircraft design increasingly followed familiar patterns. A fuselage carried crew and payload. Wings produced lift. A tail stabilized the aircraft. This configuration had won races, crossed oceans, and proven itself reliable to pilots and generals alike. Against this background of standardization, Jack Northrop pursued an idea that questioned the very geometry of flight. He believed the conventional airplane was compromised by unnecessary parts, and that its basic layout was inefficient. Northrop was not an outsider to aviation. Born in 1895, he entered aircraft design during the earliest decades of powered flight. He worked with major firms including Lockheed and Douglas, gaining deep experience in structural design and production realities. By the late 1930s, he was an established figure in the industry, respected for his technical competence rather than radical thinking. Yet beneath this conventional resume lay a persistent conviction. Removing the fuselage and tail could unlock the true aerodynamic potential of an aircraft. The concept was simple in theory, but disruptive in practice. A traditional airplane carries lift-producing wings attached to a drag-producing body. Northrop questioned why lift and payload needed to be separated. If the entire aircraft were shaped as a single wing, drag could be reduced, structural efficiency improved, and range dramatically increased. Fuel, crew, and engines would all be embedded within the wing itself. What Northrop envisioned was not an abstract concept, but a practical machine built around aerodynamic efficiency. This idea was not born from speculation. Northrop conducted mathematical analyses and wind tunnel testing to support his claims. His studies showed that a flying wing could outperform conventional designs in lift-to-drag ratio, especially for long-range missions. For military planners beginning to think in terms of intercontinental distance, these numbers were significant. Efficiency meant range. Range meant strategic reach. On paper, the flying wing was not merely different, but superior. Yet theory collided with habit. Pilots distrusted aircraft without tails. Military procurement officers favoured configurations they understood. Stability was a central concern. Conventional aircraft relied on horizontal and vertical stabilizers to correct motion. Without them, control depended on subtle aerodynamic balancing and pilot input. In the 1930s, before electronic flight computers, this posed serious challenges. Northrop acknowledged these risks, but believed they could be managed through careful design. As war approached, the United States accelerated its aircraft programs. Northrop Aircraft, the company he founded, contributed to the broader wartime effort by producing conventional military aircraft. This work tied Northrop directly to the Second World War, not as a combatant, but as an engineer supporting industrial mobilization. Factories associated with his firm built aircraft components and operational designs that aligned with immediate military needs. The flying wing, however, remained on the margins, seen as too experimental for mass deployment during wartime. Despite this, Northrop continued to pursue the concept quietly. Experimental aircraft such as the N1M demonstrated that tailless designs could fly in controlled conditions. These tests were incremental, focused on stability and handling rather than performance records. The results were promising, but not decisive. Without modern control systems, pilots had to constantly correct the aircraft, and even minor miscalculations could lead to instability. To Northrop, these were solvable engineering problems. To military officials, they were unacceptable risks. World War II reinforced conservative decision-making. Aircraft programs favoured designs that could be produced quickly, maintained easily, and flown reliably by thousands of pilots. Radical experimentation gave way to proven templates. Northrop's flying wing did not disappear, but it was postponed. The war effort demanded certainty, and certainty favoured convention. Still, the data Northrop gathered during this period laid the groundwork for something larger. By 1945, the war ended with American industrial dominance firmly established. The transition from wartime urgency to post-war planning reopened doors for experimental concepts. Long-range strategic bombers became a priority as the geopolitical landscape shifted. Suddenly, efficiency and range mattered more than ever. Northrop's flying wing, once considered impractical, reappeared as a potential solution to emerging strategic needs. Yet, even as interest grew, resistance remained strong. The flying wing challenged not only aircraft design, but institutional comfort. It required new training methods, new testing protocols, and a willingness to accept unfamiliar risk. Northrop stood at the intersection of proven capability and unaccepted innovation. He had not failed to make his aircraft fly. He had succeeded in doing so too early. If you appreciate documentaries that explore how engineering ideas confront institutional limits and historical timing, remember to like the video and subscribe to the channel for more deep, fact-based stories. As the United States entered the post-war era, Jack Northrop faced a defining moment. His idea had survived mathematical scrutiny and physical testing, yet acceptance remained elusive. The flying wing promised more than incremental improvement. It proposed a redefinition of flight itself. The question was no longer whether his aircraft could fly, but whether the world was ready to trust a shape that defied everything aviation had become. United States 1946. Victory in World War II did not bring freedom of experimentation. It brought scrutiny. As the United States shifted from wartime production to post-war strategy, military aviation entered a period of consolidation and political calculation. Budgets tightened, priorities hardened, and experimental programs faced harsher judgment. For Jack Northrop, this moment should have marked the arrival of his life's work. Instead, it became the beginning of its rejection. Long-range bombing dominated post-war thinking. The newly independent US Air Force wanted aircraft capable of carrying heavy payloads across intercontinental distances. On paper, Northrop's flying wing was perfectly suited to this mission. It offered exceptional range, high-altitude performance, and structural efficiency unmatched by conventional bombers. These requirements led to the formal development of the XB-35, a massive piston-powered flying wing designed to serve as a strategic bomber. Technically, the XB-35 was ambitious, but grounded. Its span exceeded most existing bombers. Engines were buried within the wing to reduce drag. Control surfaces replaced a traditional tail, using elevons and split flaps to manage pitch, roll, and yaw. Yet, even as the aircraft took shape, problems emerged. The complexity of its propulsion system caused delays, and maintenance proved difficult. Meanwhile, aviation technology was changing faster than any designer could predict. The arrival of jet propulsion reshaped priorities almost overnight. Piston engines, no matter how refined, were becoming obsolete. To keep pace, Northrop's team converted the flying wing into a jet-powered version, the YB-49. In theory, the transition preserved the advantages of the design while modernizing its propulsion. In practice, it exposed deeper challenges. Jet engines magnified stability issues that pilots had previously managed at lower speeds. Flight testing produced mixed results. The YB-49 demonstrated impressive speed and altitude performance, but it remained difficult to control. Without computerized flight assistance, pilots had to constantly correct the aircraft's behavior. Minor disturbances could amplify quickly. Accidents followed, including a fatal crash that deeply affected Northrop and reinforced doubts within the Air Force. Each incident shifted perception further away from innovation and closer to risk avoidance. Technical difficulty alone did not decide the program's fate. Politics played an equally powerful role. Competing aircraft manufacturers promoted more conventional bombers that promised reliability and faster deployment. The strategic environment of the early Cold War favoured certainty over experimentation. Military leadership sought systems that could be integrated quickly into established doctrines. The flying wing demanded new thinking, and new thinking carried institutional cost. By the late 1940s, pressure mounted to cancel Northrop's program. Despite continued refinement and strong theoretical performance, confidence eroded. In 1949, the flying wing bomber projects were officially terminated. Northrop Aircraft was ordered to destroy remaining airframes. For Jack Northrop, this moment represented more than professional disappointment. It was the collapse of an idea he had pursued for decades. The cancellation devastated him. He believed the decision was not purely technical, and history has supported that view. Decades later, declassified documents and testimonies revealed that the Air Force acknowledged the flying wing's aerodynamic advantages. The barrier had been control, not concept. Without computers to stabilize flight, the technology of the era could not safely unlock the design's potential. After the program's termination, Northrop withdrew from active aircraft innovation. He sold his company's interests and retreated from public engineering life. Unlike many industrial figures, he did not reinvent himself within management or consultancy. His silence reflected both disillusionment and realism. He understood that his idea required technologies that did not yet exist. The post-war period closed with an irony few recognized at the time. The United States rejected the flying wing, not because it was flawed, but because it was premature. Stability algorithms, digital fly-by-wire systems, and advanced materials were decades away. Without them, Northrop's design remained incomplete, not in theory, but in execution. By the early 1950s, his vision had been archived as a failure, yet the principles survived quietly within research papers, test data, and institutional memory. The shape that had been dismissed did not disappear. It waited. The central question left hanging was simple and unresolved. Did Jack Northrop fail to build a viable aircraft, or did aviation fail to reach the technological moment his idea demanded? United States, 1974. Jack Northrop was in his late 70s when the world finally began to change in his favour. He no longer ran an aircraft company. He no longer designed prototypes. His flying wing had been absent from active development for more than 2 decades. And yet, inside classified research programs, the very limitations that once doomed his work were disappearing. Digital computers were entering aircraft design. Control theory was being translated into hardware. For the first time, machines could correct instability faster than any human pilot. What had defeated the flying wing in the 1940s was no longer present. A fly-by-wire systems transformed control from physical linkage into mathematical command. Computers could sense minute deviations and compensate instantly. This single shift altered the balance between aerodynamics and stability. Shapes that had once been uncontrollable became manageable. Designs that had required constant correction could now fly smoothly, quietly, and safely. At the same time, military priorities were evolving. Detection had become as important as speed or payload. Radar systems improved rapidly, and survivability depended increasingly on minimizing visibility rather than maximizing power. Engineers began to rediscover an old truth Northrop had emphasized decades earlier. Shape mattered. Smooth surfaces, blended edges, and continuous contours reflected less radar energy. The flying wing was not only efficient, it was inherently difficult to detect. In the late 1970s, the US military began exploring stealth aircraft concepts in earnest. Classified programs examined radar signatures, materials, and geometry. Many conventional aircraft shapes failed these tests. The flying wing, by contrast, excelled. Without vertical stabilizers or protruding fuselages, it presented fewer reflective angles. What had once looked strange now appeared logical. Engineering priorities had caught up to Northrop's thinking. Northrop Corporation, the company that still bore his name, was invited to participate in these programs. engineers working decades after Jack Northrop's active career began studying archived data from the XB-35 and YB-49. Wind tunnel results, stability analyses, and performance predictions that had been dismissed now proved valuable. The past re-entered the present not as nostalgia, but as evidence. The result was the development of the B-2 Spirit. Though radically more advanced in materials and electronics, its fundamental shape traced directly back to Northrop's original concept. The aircraft embodied everything the flying wing had promised: long range, high efficiency, exceptional stealth, stability achieved through computation rather than compromise. It was not a modified conventional aircraft. It was the flying wing realized at last. Jack Northrop lived long enough to see this vindication. In private demonstrations, he was shown images and models of the B-2. Those present later described his reaction as subdued but emotional. He recognized the aircraft immediately. The shape was unmistakable. The technology was new, but the idea was old. It was his. This moment revealed a deeper truth about technological progress. Northrop had not been wrong. He had been early. His failure was not conceptual, but temporal. Engineering had rejected his design not because it violated physical laws, but because it required tools that did not yet exist. Once those tools emerged, his solution became not only viable, but superior. The long-term impact of this realization reshaped American military aviation. Flying wing principles extended into future programs, including unmanned systems and next-generation bombers. The B-21 Raider, developed decades later, further refined the concept. Each iteration validated the same foundation: efficiency through shape, stability through computation, stealth through geometry. Northrop's legacy was never about winning contracts or dominating headlines. It was about redefining the parameters of possibility. He challenged the assumption that aircraft design had reached maturity. He demonstrated that convention could be the greatest obstacle to progress. In doing so, he exposed a pattern common in engineering history. The most disruptive ideas often fail not because they are incorrect, but because they demand ecosystems that do not yet exist. Unlike many innovators, Northrop did not chase public recognition. He did not write memoirs claiming injustice. He left behind test data, designs, and a question: what if the future refuses to arrive on schedule? His life offered an answer. It will eventually arrive anyway, carrying older ideas with it. For modern engineers, Jack Northrop represents a caution and a lesson. Technology advances unevenly. Materials, computation, doctrine, and culture rarely evolve together. Vision sometimes outruns infrastructure. When that happens, progress pauses, but it does not vanish. It waits. If this documentary helped clarify how long-term engineering ideas survive rejection and return stronger, consider liking the video and subscribing for more history, grounded in technical reality rather than myth. Jack Northrop never lived to see the full implications of his work extend into the 21st century, but his influence remains embedded in the silhouettes crossing modern skies. The flying wing did not replace every airplane, nor was it meant to. It redefined what was possible once technology caught up with imagination. The final question is one that extends beyond aviation itself. How many transformative ideas are currently being dismissed? Not because they are wrong, but because their time has not yet arrived.